Hey everybody, it's Thursday, October 29th. As you can see here in the aim today, our goal for this video is to establish the relationship between force and acceleration. Before we do that though, I would like to revisit what we discussed yesterday, which was all about Newton's first law. Now, yesterday when we talked about Newton's first law, we outlined the basic details of Newton's first law that, it describes how objects move essentially and how their motion can relate to forces that are acting upon them. We also established the idea that the inertia that an object has is its resistance to its acceleration, and we talked about how an object's inertia can be indirectly measured through its mass. And all that stuff is pretty basic and straightforward and probably sounded pretty familiar to you based on what we talked about in honors physics. Having said that, what I want to do here in the beginning of this video is take a look at a problem which reveals something extremely important about Newton's first law. And so I'm going to put this question up on the screen. I'd like you to take a look at it and think about it, and then we'll go over it. This question here, which is in Newton's packet, it's on page 1, number 1. It says, why does a child in a wagon seem to fall backward when you give the wagon a sharp pull forward? I want you to take a second to pause this video here and answer this question. And when you hit play, we'll talk about it. So, in thinking about this question, why does a child seem to fall backward when you give the wagon a sharp pull forward? I'm sure a lot of you arrived at an answer. And the answer is when you have the wagon and you have a kid like sitting in the wagon. Oh, dear God. That when this person is sitting in the wagon, before it's given a sharp pull forward, the wagon is at rest. And because the wagon is at rest, so is the kid. But when the wagon gets a sharp pull forward, the friction between the kid's legs and backside, if you will, pulls the bottom of the child forward. But because the top of the kid, namely their head and their arms, whichever part of them is not directly touching the wagon, that part of them is at rest. And so, according to Newton's first law, it has a tendency to remain at rest. And so, relative to the bottom of the wagon, their head and the rest of the top of their body moves backwards. And that seems to make pretty good sense. That because the kid is at rest, they have the tendency to remain at rest relative to the surface of the wagon. And then because the wagon moves forward, the person moves backwards. It's important to realize when you're standing on the subway, it's the same thing, right? You get on the train, you're standing there, the train starts, and if you don't have your legs underneath you, usually this is a pretty good way to tell who's a tourist in New York, right? That they fly backwards when the train moves forward because they were at rest. They have a tendency to remain at rest. The friction drags their feet forward while leaving the top of their body at rest. And so they end up taking on this diagonal stance, which causes them to fall backward a little bit. But the answer to this question is much more nuanced than that. Unfortunately, the answer is, as was the case yesterday for a question we looked at, the answer is, it depends. But this is fairly clear because what it depends on is something very specific, which is something we're going to make totally clear in all these problems we're asking about. The answer, it depends, needs a little more clarification, but the answer, it depends, of course, is it depends on who you're asking. Are you asking me, standing to the side, watching this kid fall backward in the wagon? Or are you asking somebody else miniature sized, I guess, standing in the wagon watching what's happening to this kid. It depends on the observer. And this is an extremely important and confusing point that we're about to go through here. So I'm going to try to break it down as much as possible. But it's important to realize you all have familiarity with this. If you've ever been standing on a train and fell backward when it began its motion, or if you were standing on a train and fell forward when the train began to stop. So if the train had an acceleration in the opposite direction of its velocity, you would accidentally tip forward. This is something that I'm sure you've all experienced riding the bus or the train before. So the other day, now we're going to have to sort of really break this down. So I'm going to bring up something I talked about the other day. The other day, we talked about inertial reference frames, but we didn't get a chance to talk about non-inertial reference frames yet. And so now we really want to tie all of this together. As we said the other day, an inertial reference frame is a reference frame that is at rest or moves with a constant velocity. Remember, the usage of the word reference frame I always found to be super confusing when I was first taking physics, but I think it's important to realize when we use the term reference frame, we're really just talking about any object or thing or entity to which the motion of another object can be referenced. So essentially what we're saying is that, like, if you're standing on the ground watching a car drive by on the street, your reference frame is from the ground. So like the ground is your reference frame. You're just standing there on the ground watching what happens. It's important to realize the person in the car, as they're looking at you, as they pass you, is in the reference frame of the car. That's what we mean. And so if the car is driving at a constant velocity and you are standing there on the ground at rest, you are both in inertial reference frames. They're reference frames that move at a constant velocity. On the other hand, there are reference frames that we can refer to as non-inertial reference frames. And I'm sure you can figure out what a non-inertial reference frame is if you look at the definition of an inertial reference frame. Because if it's not at rest or it's not moving with a constant velocity, then it's accelerating. So a non-inertial reference frame is a reference frame that is not at rest or moving with a constant velocity. These kind of reference frames are sometimes called accelerated frames because clearly if it's not at rest and it's not moving with a constant velocity, then it's accelerating. Take a moment to pause this video here and write that down because this distinction is extremely important and relevant to the question that we just tried to ask. When you hit play, we'll tackle this question directly. So the thing about non-inertial reference frames is Newton's first law does not work in non-inertial reference frames. Newton's first law only works in inertial reference frames. If the reference frame in the problem is not an inertial reference frame, then Newton's first law does not apply to that situation. And so the example that we'll use, because I think it's a pretty clear example, and it's important to realize any of the examples that I've already mentioned, the subway, the person sitting in the wagon, the example we'll use here is a person sitting in a car. So there is the seat in the car, and here's like the dashboard of the car. And let's imagine the car is stopped, and there's a cup of coffee. Oh my God. Sitting on the dashboard of the car. And then the person who's driving the car, once the light turns green, boom, steps on the gas. The coffee cup is going to spill all over the person in the front seat. And of course, now the whole point of this, as we mentioned before, is that how we describe the motion of the coffee cup depends on who you're asking. And so the first thing that we should say here about non-inertial reference frames is that in an accelerated reference frame, sometimes the motion of objects will appear as though they are caused from some force. But really, are just a product of the fact that the frame is accelerated. And a good example of this is the coffee cup on the dashboard, or the sliding backpacks in the school bus in the problem we saw yesterday, or the kid in this wagon, or the person on a train. So the idea is you have to put yourself in the position of the person in the reference frame that is accelerating. If you're in the position of this person sitting in the car, it's important to realize when you're in any reference frame, everything in your reference frame is at rest, right? Imagine putting something in your cup holder in your car and then driving along at a constant velocity. Somebody standing on the side of the road would see you, the car, and the water bottle or coffee cup or whatever was sitting in your cup holder moving by them at a constant velocity. But when you look down at your cup holder and you see the object is always just sitting there next to you at rest. So everything in your reference frame is at rest. And maybe we should write that down also because that's very important to help understand this. And so let's write here, everything in your reference frame is at rest. And so if you're sitting in this chair, I want you to imagine this. You're sitting in this chair, and all of a sudden, the cup of coffee comes flying at you. How do you explain the motion of the coffee cup? Well, you'd say first the coffee cup was at rest, and then all of a sudden it was flying toward me. Or it accelerated from your vantage point. And so you would say, well, since the coffee cup was not flying towards me and then all of a sudden was flying towards me, it accelerated. And the only way the coffee cup could accelerate is that there must have been a force acting on it. And so it's important to realize here, essentially what we are getting at is that observers in different reference frames see things differently. We talked about this when we were talking about relative velocity. The way velocities are measured depends on who you ask, and the way that objects' motion is observed also depends on who you ask. Now, we can help to make sense, I think, of what this person sitting in the car sees if you think about what somebody standing on the side of the road sees. So somebody standing on the side of the road sees a pretty simple situation. They see the coffee cup at rest. They see you at rest. They see the whole car at rest. And then all of a sudden the car starts to move forward. And so essentially what they see is not that the coffee cup started flying towards you, but that you started flying towards the coffee cup, because the coffee cup was at this particular location in space. But then you, the car, and the dashboard moved forward, and now the coffee cup had nothing holding it up. And so it basically just fell into your lap. Newton's first law works for the person who is standing on the side of the road because they are just standing on the side of the road. They are in an inertial reference frame. But for you, essentially what we're saying here is how you observe what happens to the coffee cup distorts your perception is distorted because of the acceleration. That's the idea. The very fact that you are in an accelerated reference frame is distorting your perception and making what you sense and observe different from what the person in an inertial reference frame is observing. And so the person who is standing in the inertial reference frame just sees you fly towards the coffee cup, but because in your reference frame, you are still at rest, and they are still at, and by they I mean the coffee cup. The coffee cup is still at rest, and it's actually in your reference frame, this person on the side of the road who's moving backwards. The only possible way you could explain the motion of the coffee cup is that it was at rest, and it's not anymore, so there must have been a force pushing it toward me. So what we'll say here is that, however, an observer in an inertial reference frame will see the motion as a result of the object's inertia. The coffee cup's inertia, its tendency to stay at rest while you're flying toward it, is why the coffee cup spills on you, not as the result of the action of a force. So there's a disagreement between an observer in an inertial reference frame versus an observer who's not in an inertial reference frame. And so what we're getting at here is that while there is actually no force acting on the object, causing it to move, the only way the observer in the accelerated frame or in the non-inertial reference frame can explain the object's motion is essentially to invent a force. It's to say, well, there must have been some force acting on it because otherwise physics is broken. The thing wasn't moving and now all of a sudden it is. And these invented forces are called fictitious forces. And that's true because they only exist in the accelerated reference frame. Now, whether you believe it or not, you've already heard of, probably, a fictitious force. If you've ever been in shop and heard of the centrifugal force, or as people like to mispronounce it, the centrifugal force, that's a fictitious force. And we're going to get to that when we get to circular motion. But the idea is essentially because like a propeller is experiencing circular motion, technically like the tip of the propeller is accelerating because the direction of its velocity is changing. And so anything that is observed from the point of view of like the tip of the propeller is in a non-inertial reference frame or in an accelerated reference frame. And so the only possible way you can explain things in an accelerated reference frame is to make use of these fictitious forces. This is extremely confusing. It will confuse you now, and it will confuse you when we talk about circular motion. The goal is to expose this to you as much as possible so that by the time the AP test comes up, you'll be in pretty good shape to understand it and explain it if you have to. Full disclosure, I thought I understood this pretty well when I was a student. I only realized when I started teaching this course 6 years ago that I did not have that great of a grasp on this because I found it was a very difficult time explaining this the first time I ever had to explain it because you really need to understand things to be able to explain them. And so that's why I'm going to try my best to put you in situations where you have to explain these things because that, I think, will force you to master the concept. This is a lot of words. I'd like you to take a minute to pause this video here and write this down. And when you hit play, we'll move on. Okay, so just to tie this before we wrap this up here, just to tie this back to the question we were originally looking at, we were talking about this kid in a wagon falling backward when the wagon was given a sharp pull forward. The answer, as we said, was it depends on whom you ask. If you are asking somebody standing on the side of the road, they say, well, the top of their body was at rest. It had a tendency to remain at rest. Everything else connected to the bottom of their body moved forward. Their head stayed at rest relative to the bottom of their body, and so that's why they fell backwards. But for an observer standing in the wagon, which is an accelerated reference frame, they would say, well, the person is at rest in the beginning, and they're still at rest with respect to me at the end, but the top half of their body all of a sudden flew backwards this way. And so the only way that they could explain the top half of the person's body being at rest and then all of a sudden flying backwards is to say, well, there must have been some force that pushed their body backwards. That force, as we said, is called a fictitious force. And the reason why we call it a fictitious force is because it doesn't actually exist, but it is the only possible way that somebody in an accelerated reference frame could explain the motion of the objects. But here's the deal. While on the homework solutions that you will see for questions that are kind of like this, while I'm going to explain it both ways in those homework solutions, it's very important to realize that one of the conventions on the AP test, the first one, in fact, says the frame of reference in any problem is assumed to be inertial unless otherwise stated. So, even if they ask you to consider the forces acting on something like the kid in the wagon, acting on the person in the wagon, and the wagon is accelerating, unless they explicitly tell you to consider it from the point of view of the person in the wagon in the accelerated reference frame, the frame is inertial. And so really what they want you to do is to consider the forces from the point of view of a person standing off to the side on the ground. That's the idea. Convention number 1 says the frame of reference in any problem is assumed to be inertial unless otherwise stated. And that's it for non-inertial reference frames. It's a lot, and that's why I didn't want to attach this to yesterday's video, because it is confusing. And like I said, hopefully when you get practice with fictitious forces on the regular forces homework, and then when you get the practice with them again on the circular motion homeworks, you'll start to get a little better of a grasp on it. These things are confusing. They take time to assimilate into your understanding. And with that, that actually finishes up Newton's first law. And so, of course, that brings us to Newton's second law. Okay, so Newton's second law is pretty straightforward. What you're going to see, though, in this course is that we take Newton's second law way deeper, way deeper, in much more detail than we ever did in the honors class. We're going to learn a whole new framework for solving Newton's second law problems. Of course, we still have to work up to that a little bit, but nonetheless, I want you to keep that in mind. So the first thing that we should ask here is, what is Newton's second law? And Newton's second law is a mathematical statement, an equation, essentially, relating the force on an object, its inertial mass, and its acceleration. And so, of course, the obvious question here is, what in the hell is inertial mass? This is an annoying thing. I never heard the phrase inertial mass until I started teaching this course, because most physics courses never cover this idea. And that's because it's totally worthless to do so. But because the whole focus of this course is to really lean into getting you to understand stuff instead of just regurgitate stuff and be able to do algebra, those who wrote this course decided that they wanted you to really understand the foundations of physics. So I'm sure you all remember to some degree that there is an equation in physics called Newton's second law. I'm sure you remember what it is. I'm sure you also remember in honors physics that we covered an equation called Newton's universal law of gravitation. That equation was the force of gravity is equal to a constant, which we called big G, and then times mass 1 times mass 2 over r squared. And the confusing thing about this is when the equation has mass, we just say the equation has mass. The problem is that physicists did not know that the m in Newton's second law was the same as the m in the gravity equation. In fact, they referred to them separately as inertial mass and gravitational mass. In fact, we didn't know that these two things were exactly the same kind of mass until Einstein came along in 1915. So for not that long, we've known that these things are the same. Now, of course, since 1915, everybody just says, well, mass is mass is mass. So, like, who cares? But the AP course cares. And so we have to focus on the difference here. And so essentially what inertial mass is it's the concept of mass as being a measure of the object's inertia. And so this is going to be measured in kilograms, of course. And so essentially what we're saying is that this is the m in Newton's second law. So this is the mass of an object as related to Newton's laws of motion, especially the first and second. And that says Newton's law. So I just want to write here Newton's laws, especially the first and second. And so that's the idea. Inertial mass refers to the concept of mass as being a measurement of an object's inertia. Not to sort of spoil it, because we're not going to get to the difference between inertial mass and gravitational mass until we get to gravity, but the basic idea is gravitational mass essentially refers to how mass interacts with other masses, or how mass interacts with the force of gravity. Of course, we already know the answer is that there is no difference. But until then, we want to make sure that at least when you see the phrase inertial mass, you know it is referring to mass as conceived of in Newton's laws. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so as we said here, Newton's second law is a mathematical statement relating the force on an object, its inertial mass, and its acceleration. Of course, the obvious question here is, what does that mathematical statement say? And that mathematical statement says the acceleration, which gets the symbol a, of course, of an object is directly proportional to the net force acting on it and inversely proportional to its mass. I'm sure you remember that, but it's very important for everybody to take a minute to pause this video here and write that down, because that is crucial. And when you hit play, we'll take a look at it. So, in the Regents course, you saw in the Regents reference table the equation A equals F net over M. I thought it was kind of weird that they solved it for A in the reference table, but of course we know how to do algebra, so it doesn't really matter. The equation is F net equals MA. That is not how it's written in the AP reference table. In the AP reference table, and again, this is just something we're going to have to get used to with this reference table because things are a little different. It's written like this. But of course, because sigma, this is a Greek letter, sigma F, I'm sure you know from math, really just means sum of the forces. Essentially, that means the same thing as F net over M. And so that's why in the AP reference table, the equation is printed like this. And notice here, they're just showing you these arrows because force and acceleration are vectors. And they're representing vectors by putting arrows on top. Now, while the F net over M version of this is more comfortable, probably, because you've seen it before, I think thinking about this in terms of like the sigma F notation, the sum of the forces, as you'll see in a couple of days here, is actually going to be really important. Because if you remember, I began our discussion of Newton's second law here like 5 minutes ago by saying that the framework that we're using to analyze these problems is totally different in this course. And so thinking about it as the sum of the forces, I think is going to be extremely useful. And so I'm going to write here sigma F, which is equal to F net, is the sum of the forces slash the net force. And that, of course, is measured in newtons, as I'm sure you remember. M in this equation, as we alluded to before, is the inertial mass, which, of course, if you refer to it as mass, that's totally fine. Basically, what I want you to be aware of right now is that when you see the phrase inertial mass, that you are understanding that it means it's the M in this equation, Newton's second law. And then lastly, we have our A here, the acceleration, and that, as I'm sure you all know, in units of meters per second squared. And so what we'll write here, just off to the side, because this is the first time we've seen a Newton this year, is that the net force is equal to M times A. And so that means the unit of force has the unit of mass times the unit of acceleration. And so what that means is 1 Newton is equal to 1 kilogram meter per second squared. And so, of course, just to put a pin in this before we wrap it up, the way that you get the units of acceleration from this to be meters per second squared is because you have newtons divided by kilograms, which means you have a newton, a kilogram meter per second squared, divided by kilograms. And so the kilograms cancel, leaving you with meter per second squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so I just want to take a second to address this sum of the forces thing before we move on, because obviously this is going to come to play in a ton of these problems, especially based on what we said in the video before the Newton's first law video. So the key concept here is that forces, which are vectors, combine like all other vectors. So forces which act in the same direction or in the opposite direction should be added with the signs. Pretty straightforward. Forces which act at right angles should be added, and I put added in quotes here because you're not actually adding, you're doing the Pythagorean theorem, but they should be added using the Pythagorean theorem. And, as we said in this video a few days ago, forces which act at any angles other than 0 degrees, 180 degrees, and so those are equal in the same direction or in opposite directions, or 90 degrees at right angles, should be added using the component method, the method for vector addition that we developed in the video the other day. Take a second to pause this video here and write that down, because that'll prove itself to be very important when we get into a lot of problems this year. So, last thing, before we take a look at a problem, very important for everybody to realize here, based on Newton's second law now, we could especially tie this into Newton's first law. Essentially, Newton's first law and Newton's second law are saying the same thing. They're just saying that a little differently. One says it with words, the other says it with an equation. Motion can exist without forces. Forces only cause changes in motion or accelerations, since objects can move as a result of their own inertia. Take a second to pause this video here and write that down. When you hit play, we'll take a look at a problem. Here's an example of a problem. Pretty straightforward. This is in Newton's packet on page 12, number 11. It was chopped up, like went from the top of the page to the bottom of the page in different columns. So I just decided to type it here. It says a boat moves through the water with 2 forces acting on it. One is a 2,000 Newton forward push by the water on the propeller, and the other is an 1,800 Newton resistive force due to the water around the bow. And part A here says, what is the acceleration of the 100-kilogram boat? Parts B and C are classic, like college physics textbook questions, which say, now that you found the acceleration using methods for forces, let's bring this back to the previous chapters and let's talk about how we can use the kinematic equations to solve for other things. Let's forget about that for right now. Let's focus on part A. Part A is asking, what is the acceleration of the 1,000-kilogram boat? Based on everything that we've said so far, and the fact that you have done this before, problems exactly like this in Regents physics, I suspect you should be able to solve this without having to see a solved example of it first. So I'd like you to go ahead and pause this video here and give this one a try on your own. The numbers here are pretty basic. So go ahead and pause this video, answer just part A, and when you hit play, we'll go over it. Okay, so the first thing you may have realized in trying to solve for the acceleration of this boat here is that it probably might have been helpful to draw a diagram for this problem. And you'll see this come into play a heck of a lot here in this unit. So it says here we've got this forward force, we'll just assume the boat is going to end up moving this way, of 2,000 newtons. And we have this resistive force, which it should be clear means that's going in the other direction, of 1,800 newtons. So I'm going to say here that F1, and I'm just going to say that's going to the right, so I'm going to call that positive 2,000 newtons. And F2, because it is going to the left, is negative 1,800 newtons. They also tell us here in this problem that the mass of the boat is 1,000 kilograms. And so I'm going to write M is 1,000 kilograms. And I'm looking for the acceleration. So in order to solve for the acceleration, you have to know the sum of the forces, and you have to know the mass. We have the mass, but we don't yet have the sum of the forces. And so it's important to realize here, and as is the case in all problems really, the sum of the forces equation is dictated by the orientation of the forces. These forces are in opposite directions. So as we just said, you add with the signs. And so here we'll say the sum of the forces is F1 plus F2. And so that means the sum of the forces is going to be 2,000 newtons plus negative 1,800 newtons, which gives us a total force, or net force, of 200 newtons. And because Newton's second law says the acceleration is equal to the sum of the forces over the mass, I now know the sum of the forces is 200 newtons, and I divide that by the mass, 1,000 kilograms, and that gives me an acceleration of 1/5. 200 is 1/5 of 1,000, and so that would be 0.2 meters per second squared. And that's it for part A. Now, I just want to address one thing, because some of you might have done this a different way. I decided to show it like this because this is the first example that I was ever going to show. But it's important to realize I am totally fine with you doing something that looks like this and just plugging the sum of the forces equation directly in to the acceleration equation. That is totally fine by me, and doing this in one step, because they did not actually ask you for the sum of the forces. They just asked you for the acceleration. And so doing it like I showed here on the bottom right-hand corner of the slide is totally fine with me. So according to the information given in the problem, this boat has an acceleration of 0.2 meters per second squared. Now, just for fun, I'd like you to go ahead and answer B and C. B and C say, for B, if it starts from rest, how far will the boat move in 10 seconds? And C says, what will its velocity be at the end of 10 seconds? I'd like you to take a minute to pause this video here and go ahead and answer B and C. So B and C are asking you to apply the kinematic equations. We've got 10 seconds given in the problem here. So we're trying to find out how far the boat moves and what its velocity will be if it starts from rest. And so for part B, we have here the initial velocity is 0. We know the acceleration, because we just found it, is 0.2 meters per second squared. And we know that the time is 10.0 seconds. And this question is asking us here for how far the boat goes. We could say its displacement or its distance. It's going in a straight line. It doesn't really matter. Delta x. And so the best equation to solve for this here, in my opinion, is delta x equals v naught t plus 1/2 at squared. And I think that's the best equation because it's simple. Because the initial velocity is 0, the v naught t term goes away, and we're left over with delta x equals 1/2 at squared. And so delta x is going to be 1/2 a, 0.2 meters per second squared, times t squared, which is 10 seconds. 10 seconds, and then we got to square that. And so taking a look at the math here, we have 10 squared is 100. 1/5 of 100 is 20. And then half of that is 10. And so the displacement here is going to be 10 meters. Pretty straightforward there. They love these kind of questions because they say that this is like you synthesizing your understanding from two separate units, regular kinematics and dynamics here now that we're talking about forces. And so there are a lot of ways that you could do C. I like to do all these parts not using my answer from previous parts if I don't have to, just because like if you made a mistake with that, your calculation for C would be corrupted. Whereas if you used every other piece of information besides what you found in this part, then you would be fine. So they tell me here that the initial velocity is 0, of course. The acceleration is 0.2 meters per second squared. And the time is 10 seconds. And I'm looking for final velocity. And so the final velocity here is equal to the initial velocity plus AT, right? That seems like the most straightforward way to go about that. And the initial velocity here is 0, so we can just get rid of that. And we have the final velocity is the acceleration times the time. And so in a rather straightforward way here, we have the acceleration 0.2 meters per second squared times the time of 10.0 seconds. And when you do that math, 1/5 of 10, of course, is 2 meters per second. And that's it. Tying this stuff together with kinematics is nice. It's simple. It's clean. Gives you a good way of looking at the problem. And so you can expect to see a lot of those as we go forward. Of course, the problems can get a little more difficult. And the harder version of these problems could look at a little something like this. This one is in Newton's packet, page 12, number 12. It says here 2 forces are applied to a car in an effort to move it. And there are 2 parts. The first part is what is the resultant of these 2 forces? Part B says if the car has a mass of 3,000 kilograms, what acceleration does it have? Now, if you notice, these forces are not in the same direction. They are not in opposite directions. And they're not separated by 90 degrees. So, you have to combine them using the component method. Something that I showed in a video, but never collected anything from you because I figured it was kind of hard, at least the first time you saw it, and that leaves me with pretty much no sense of how you're able to deal with that. So, what I'd like you to do for today's assignment is to do part A of this question. We'll save part B for tomorrow. Part A of this question asks you, what is the resultant of these 2 forces? And what I'd like you to submit to me is a picture of your work with the solution for the resultant force when they're oriented in the problem like this. In tomorrow's video, I'll start by going over that. Really, I just want to take a peek at your work to get a sense of how you're all doing with it. And then we'll go ahead and answer part B before we move on to some other forces problems. And that's it for today. So I look forward to your submission for the resultant force here, the net force, the sum of the forces, however you want to call it. And we will dig back into this problem tomorrow. Have a good one, everybody.